Hello everyone. Now that we have understood the physical concept and importance of critical radius of insulation, then it becomes very important to understand it in numerical terms, in terms of operating parameters of that steam pipe or that particular composite cylinder or composite sphere. So firstly, we are going to determine the critical radius of insulation for a cylindrical arrangement. So for this purpose, we are going to consider a cylinder. So for this cylinder there will be some internal radius, there will be some external radius, and of course the outside of this cylinder will be exposed to some fluid. There will be some length of the cylinder that we are going to consider, and then there will be some external radius, there will be some internal radius. This will be R1, this will be R2, some K will be conductivity of material of cylinder. Now let us say this cylinder is exposed to some fluid T infinity and heat transfer coefficient H on the outside, so that heat loss can take place because of convection. Obviously, there will be some internal temperature T1 on this side and there will be some external temperature T2. So now we will start constructing the thermal network. So what we see here, we will not consider this internal convection resistance. It is not necessary because we are more bothered about the thickness of insulation on the outside. So we will start from T1. So this is our T1 up to T2. It will have the first conduction resistance. Because it is conduction resistance, so that's why this will be R cylinder, and between T2 and T infinity there will be convection resistance. So between T2 and T infinity there will be convection resistance. We will call it only RC. You can add multiple layers if you want, but the result is not going to change. So we are only concerned about the immediate layer of insulation and the atmospheric resistance or convection resistance. Now we will write down the equation for heat transfer. We know that the equation for heat transfer is, in its basic form, is delta T upon summation of all the thermal resistances. In this case, this is the total delta T, T1 minus T infinity. So that will be T1 minus T infinity divided by all the thermal resistances which will come in picture. First is conduction resistance of cylinder. Second one is the convection resistance of outer atmosphere or outer fluid. So R cylinder plus R convective. This is Q. Okay. Now, how do we quantify them? We know that it can be quantified as T1 minus T infinity divided by the resistance of cylinder is nothing but ln of R2 upon R1 divided by 2 pi Lk plus the convective resistance of cylinder is 1 upon HA. So that is 1 upon H into the external surface area. So that is equal to 2 pi RL, but the difference is that this will be 2 pi R2L. Why? Because we are talking about the external surface area. Okay, now the equation has been established. Even if you have this diagram now, it will not make any difference. So, we will focus on limited things right now. Alright. Now, what do we see over here? Because we are talking about critical radius of insulation, and the heat transfer rate directly changes with critical radius of insulation. It means that this Q is direct function of the outer radius of that particular cylindrical arrangement. So that's why R2 is the governing parameter. Now in this equation there is one more parameter R1. R1 is the internal radius of that pipe or cylinder, which is not going to change. But R2 can change. Why? If we apply more and more layers of insulation, then R2 will increase. And that's why R2 is the variable which will govern, which will affect the entire heat transfer rate. And that's why if we want to determine the external radius of insulation, which will prove as critical radius, we need to differentiate this equation with respect to R2, because at a critical radius of insulation this heat transfer rate will be maximum. And that's why when we will differentiate this Q with respect to R2 only, and this should be equal to 0 for maximum heat transfer rate. That is the logic. This is the physical reasoning because of which we are not differentiating this heat transfer rate by R1, but we are differentiating it with respect to R2 and not R1. Okay. Then when we differentiate, what we get? Now let us look at this equation once. This T1 minus T infinity, these are constant temperatures. They are not going to change. They will not change with R2. That's why they are constants. R1 is a constant radius, it will not change. 2 pi L, 2 pi L, again these are constants, these are not going to change. So we can directly take them outside. So the term which is actually going to affect the heat transfer rate is this one, ln of R2 by R1 upon K plus 1 upon H into R2. So what we will do, instead of differentiating everything, we will differentiate only those parameters which actually participate in heat loss. So that's why we can say that d by dR2 of the term become ln of R2 by R1 divided by K, because these three quantities are constant, plus from the second term we have 1 upon H into R2. So 1 upon H into R2, we can directly differentiate that. So now we will differentiate only this much part, and afterwards we will equalize, we will compare it with 0 for the maximum heat transfer. So now let us start differentiating. Again, conductivity K is a property of material, so what we need to do, it will not undergo differentiation, so it needs to be taken out from the differential sign. Now ln of R2 by R1, as we know, differentiation of ln of x is 1 upon x. So differentiation of ln of R2 by R1 will be 1 upon R2 by R1, and it is nothing but R1 upon R2, because it is 1 upon R2 by R1. So that's why it will be R1 by R2 multiplied by differentiation of this quantity also, because when we say d by dx of, let us say, ln of x, so firstly we are differentiating this, and also we can write 1 upon x into d by dx of x as well. But as this is 1, so we simply avoid it. But in this case we cannot avoid it. So this is the differentiation of ln only, but then differentiation of this term is to be done. So differentiation of 1 upon R1 will not happen, because R1 is not dependent on R2. But differentiation of R2 will happen. Differentiation of R2 with respect to itself is 1. So that's why differentiation of this total x, this total R2 by R1 is 1 upon R1 only. Okay. Now, so we have finished with differentiation of the first term. What about the differentiation of the second term? So it will be 1 upon H as it is. If we look at it carefully, this is actually 1 upon x, and its differentiation is being done with respect to itself. So d by dx of 1 upon x, which is minus 1 upon x square, or I should write it R2 square, and it is entirely equal to 0. Okay, so now we can eliminate R1, this R1 and this R2. So what we get over here is 1 upon KR2. I can take all this negative entity on the right hand side of the equality sign. It will be equal to 1 upon H R2 square. Now simple rearrangement will tell me, I take this R2 square on this side, so one R2 from denominator and one R2 from numerator will be cancelled. It will give me only R2, which is equal to, I take this K on this side, so it will become K upon H. So I will write R2 is equal to K upon H for a cylinder, which is equal to your R critical for a cylinder. This is the mathematical formula by which you can obtain how much, after how much radius, the radius will become the critical radius of insulation, beyond which the heat transfer rate actually will reduce. Thank you.